Hello everyone, we are back again now with part 14 and today's our topic is refractive index. In the previous video we have discussed about refraction of light through a glass slab and today we'll talk in detail about what exactly is refractive index. But before we go ahead with the understanding of what is refractive index, we need to understand what are the laws of refraction. So if you remember, we have discussed about laws of reflection in one of our previous video where we have discussed that there are two laws of reflection: angle of incidence equals to angle of reflection always, and incident ray, reflected ray, and normal, they all lie on the same. So if you observe with those two if you observe with those two laws of reflection, you can see that we have one law which is common. Only in place of reflection it becomes reflected ray, it becomes refracted ray. So what are the laws of refraction? Here they are in front of you. The first one is the incident ray, the refracted ray, and the normal. So it goes like this: incident ray, refracted ray, and the normal, they all lie on the same plane. They all lie on the same plane. Second one is the ratio of sine of angle of incidence. You can see sine of angle of incidence to ratio of sine of angle of incidence to sine of angle of refraction is a constant. And when we talk about a constant, that constant is basically called as refractive index, which we represented with a symbol N like this. Now, if you refer to various books, certain reference books also represent refractive index with a symbol mu like this. But we will be using this symbol as it is given in our textbook, so we'll be using this one. So what is the refractive index? It's the ratio of sine of angle of incidence to sine of angle of refraction, and this is also the second law of refraction, which says ratio of sine of I to sine of R is a constant for light of given color and for given pair of media. Now, many a time students are not aware that what exactly is Snell's law. This second law of refraction is also referred to as Snell's law of refraction. And you can see, as it is mentioned here, the constant value is called the refractive index of second medium with respect to first medium. Now, this line, which is second medium with respect to first medium, is very important because if you interchange it, the meaning changes and the values also change. So let's go in detail about what exactly is refractive index. So you can see there are certain terms written here about refractive index: a ray of light that travels obliquely from one transparent medium into another will change its direction in such medium. So when we talk about a ray, it changes, and we have discussed and understood that why it changes, because there is a change in the speed, because there is change in the medium, and when it goes from one medium to other medium, it changes its path, and that is happening because of the change in the speed, and it bends. So the extent of bending, how much light is bending, is expressed in terms of refractive index, which is this one. Now going ahead, if you see, refractive index can be linked to an important physical quantity, which is the relative speed of propagation of light in different media. So whether the light speed is increasing or decreasing with refractive index, we'll understand that. And what it says, the refractive index of medium of material describes how fast light travels through the material. Some more points to be covered for refractive index. These are some of the common pointers which you may have understood previously also. Light propagate with different speed in different media. We discussed this when we started with the concept of refraction of light, and we know what is the speed of light in air. Speed of light in vacuum is basically 3 into 10 raised to 8 meter per second, and in air it is slightly less because of the increase in density. So it's air, it's marginally less compared to that in the vacuum, but because it's very minute difference, we consider it as same as that of the speed of light in vacuum. And what happened to the speed of light as we move from rarer medium to denser medium, glass or water, the speed of light reduces. The value of refractive index for a given pair of media depends upon the speed of light in the two media. It's a ratio of two similar quantities. So you saw it was sine I upon sine R. So these are the similar quantities, so that's why it has no unit. Now it's not that it is only indicated in terms of angle, but it is also indicated in terms of a speed of light. So let's understand how it could be represented in terms of a speed of light. So you can see on screen refractive index, and there's a diagram given on the left side. Here light is going from medium 1, which is air, to medium 1, which is glass. Now we know, as per our previous discussion, when light goes from, now this is a rarer medium and this is denser medium. So when light goes from rarer to denser, you can see it is bending towards the normal, and that has happened. You can see. Now how do we represent and how do we read it? That's also important. So it says let v1 be the speed of light in medium 1 and v2 be the speed of light in medium 2. The refractive index of medium 2. Now many a time there's a confusion. How do we remember? So whenever we are talking about refractive index, we are finding refractive index of medium where light is entering. So you can see here light is entering inside from air to water. So you are finding refractive index of water, and from where it is coming? Air. So we are finding refractive index of water with respect to, sorry, it's not water, it's glass with respect to air. And similarly, if it is water, it would be water with respect to air. So you can see refractive index of medium 2 with respect to medium 1 is given by ratio of speed of light in medium 1 to speed of light in medium 2. So if the light is coming from 1 to 2, we are finding refractive index of medium 2, which means glass. And from where it is coming? With respect to 1, and that is given by from where the light is coming, which is medium 1 to medium 2. So you can see this is represented with a symbol N21. We read it as refractive index of medium 2 with respect to 1, given to us V1 by V2. So this is formula for refractive index of light in medium 2 with respect to medium 1. This is in terms of speed of. Previously we discussed about refractive index in terms of angle. Going ahead, you can see further elaboration on the same thing. Now, why there is more elaboration is because the numericals related to this concept comes, and which are usually very easy. But as students are not able to read this clearly, they are not able to solve it because they don't get the formula correct. So what exactly has to be done here? So you can see N12. N is basically the refractive index. 1, the first number means light is going inside this. So refractive index of medium 1 with respect to medium 2. So how do we read it? As same argument, refractive index of medium 1 with respect to 2. It means light is coming from medium 2 and going into medium 1. Now, if medium 1 is vacuum or air, so let's say if light is coming from vacuum or air, then we don't have to mention it like this. Then we'll just write N1. If it is medium, sorry, for this case where the light is coming from 2. So if medium 1 is vacuum or air, other than the refractive index of medium 2 is considered with respect to vacuum, and this is called as absolute refractive index. For absolute refractive index, we don't have to write multiple terms. So if I just write N G, it means it's a refractive index of glass with respect to air or vacuum, and the formula would be VA upon VG, or because it is vacuum, we can also write it as C upon V, because C is speed of light in air or vacuum. So you can see absolute refractive index of medium is the ratio of speed of light in air or vacuum to the speed of light in given medium, which can be represented with this one. N is equal to C upon V, or we to avoid confusion, we can also write it as N is equal to VA to maintain uniformity upon V, whatever medium it is. So if it is glass, it would be VG. If it is water, it would be VW. So similarly, this was about absolute refractive index. So if the light is coming from air or vacuum to a certain medium, that's absolute. Now, if it is any medium other than air or vacuum, then it is called as relative refractive index. Now, this absolute and relative is not mentioned in the textbook, but we need to understand and we need to know also. Now, in the textbook, there's a table given which talks about refractive indexes, and all these refractive indexes are absolute refractive indexes basically. And these are with respect to, when we say absolute, with respect to air or vacuum. So you can see the first one is air. Now this table is also very important. Below the table in the textbook, it is mentioned that you don't have to by heart, but after solving multiple times numerical, we'll be able to understand what are the values. So air, the refractive index is almost 1. It's not 1 because there are some materials added, some impurities are there in air, and that's why it is denser than vacuum. If you'll observe this table, and if the questions are asked out of this given, which one has highest refractive index, that's diamond, and the least one is air. Now the question is, which is denser amongst all of them? Denser one is diamond, and the rarer one is air. So from this we also understand that higher the density, optical density, more is the refractive index. So absolute refractive index of the medium is simply called refractive index. So if you hear a term refractive index, nothing is mentioned, it means light is coming from air. So if you'll see, refractive index of water is 1.33, which is absolute refractive index. It means ratio of speed of light in air to that of water is 1.33. Now because of this table, we just got certain combinations. So if I'll ask you a question, out of fused quartz and dense flint glass, which is denser material, we can see the refractive index, and we can understand that because dense flint glass has higher refractive index, it's a denser material because the speed of light is decreasing. Going ahead, when we talk about uh, further important points, when the light is going from one medium to another and the other medium is not air or vacuum, then we call it as a relative refractive index. In that case, we write it like this, N12, and in several books you will also find it as N21 written. Somewhere you will also find like this. These are all the ways of representing refractive index, but we'll not get confused and we'll follow the textbook pattern. This is refractive index of medium 1 with respect to medium 2, which means light is coming from medium 2 and going into medium 1. And you can see here, in if it is written like this, so light is coming from the number or the medium which is written on the left side and going into the one which is on the right side. So this becomes the formula V2 upon V1. The one which is on the other end will become numerator. Similarly, when we read this, refractive index of medium 2 with respect to 1 would be V1 by. Now certain conclusions to be drawn based on our observation of refractive index. So first one is, the optically denser medium may not possess greater mass density. If you remember the first video of refraction of light, where we discussed about rarer medium and denser medium, and we understood that when we talk about density, we are not talking in terms of mass upon volume wala density. We're talking in terms of optical density, which means how much light can bend through that medium. If the medium can bend more light, it is optically denser. If it can bend less light, then it is optically rarer. So you can see, so it's not necessary that optically denser material will have high mass density also. And we have one example, which is kerosene. It is having higher refractive index, but optically, which means it is optically denser than water. But when we put it in water, we'll observe that kerosene float, which means its mass density is less than water, but that of optical density of kerosene is higher than that of the water. So never keep this in mind that mass density and optical density are same. No, they are not. So comparing two media, the one with larger refractive index is optically denser. So if you remember just now when we saw the video, when we saw the table, wherever there was greater value of the refractive index, which means it was optically denser medium. And so then diamond was highly optically denser, was having maximum optical density, and least was of air. The other medium of lower refractive index is optically rarer. So out of two medium, the one which has high refractive index becomes optically denser, the other becomes optically rarer. So example is also mentioned here. If refractive index of one type of glass is 1.52 and the other one is 1.33, 1.52 would be termed as optically denser. So then water, therefore glass is optically denser than the water. Next one, higher refractive index of a substance, more it will change the direction of beam of light. High refractive index, more bending. Keep these points in your mind. These are very important points. Higher refractive index, more is the bending of light, and higher refractive index, optically denser medium. And going ahead with the last one, if two medias are optically exactly same, then no bending occur. It means if they have same optical density, which means they are not a different material, they are the same material, and in that case no bending will happen when light passes from one medium to another medium. So this was, if you observe, we discussed in detail about refractive index. Now let's come up to a conclusion that what is the inverse of? So refractive index of light going from medium 1 to 2 is equal to reciprocal of refractive index of light going from medium 2 to 1. It means if light goes from air to water, so let's say if light goes from air to water, it bends this much. Is the reverse also true? Which means if light goes from water to air, then also it will follow the same path, which means angle of incidence will be greater in this case, and angle of refraction would be lesser in this case. Whereas for this case, angle of incidence would be greater because it's coming from angle made by, basically in any case, angle made by a rarer medium will be greater than the angle made by denser medium. So this is also called as refractive index and reciprocal of refractive index. So if you'll say, so let's say if I'll say refractive index of medium 2 with respect to 1 will be represented with V1 by V2, then the inverse will be written like this. So if let's say we take inverse of this equation, then we will get n to 1, which is same as V1 by V2. Just now we did it. So if I'll take inverse of it, I will get n, okay, 1 upon n to 1 would be V2 by V1. And now if I'll see this, I can write it as n1 2, which means V2 by V1. So if you'll see, this is V2 by V1 and this is also V2 by V1. And if we conclude, we'll get that n12 is equal to 1 upon n2 1. And that's what is situation. Refractive index of light going from medium 1 to 2 is equal to reciprocal of refractive index for light going from medium 2 to 1. And we get numerical based on this also. So you can see the derivation is explained here, that in detail. So reciprocal of the previous situation, and you can see from 1 and 2, if we combine, we get this statement, which is, if you observe the formula goes like this: refractive index of medium 2 with respect to 1 is reciprocal of the refractive index of medium 1 with respect to 2. And we can form a common conclusion in the end, that this means that light refractive index for light going from medium 1 to medium 2 is equal to reciprocal of the refractive index of light going from medium 2 to 1. Now, this was about refractive index of 1 to 2 and reciprocally equal to 2 to 1. We have another example. If we talk about glass and water, so refractive index of light going from air to glass is equal to refractive index of light is equal to reciprocal of refractive index of light going from glass to air. And you can see this is the formula. And based on this, we form the conclusion. Now, based on this, we have many numerical, and now is the time when we'll be solving numerical, but not in this video. This was all about, if you would have seen clearly, this was all about refractive index, and we have discussed in detail refractive index. The next video, yes, you guessed it correctly, we'll discuss about numericals related to refractive index. Believe you have learned something from this video. If you have any question related to today's concept, please put it in the comment box. I'll be very happy to answer those questions. In the meantime, enjoy your life and have a great time. Bye bye. Thank you.